with regards to native Python, I would like to start by discussing Python data structures. So this is the very basic of basics, and I would like to make clear that this is a problem that I've seen occurring many times, and the problem is that people tend to forget when they are writing their code some of the properties of the basic data structures of Python, or the complexity of some data structures in Python. Take for instance, if we use a list and we do something like my list is like this, and for 1,000 we can say append, let's make run int for so my list append, can do something like this. Very simple, nothing special. So we have a list with 1,000 elements, and it will be populated by random ints. And we can run this. Oops. And finally, so here we are making a list. It's a very simple example where we are making a list with 1,000 elements, and every time we want to search this list, the average case will be 500, and the worst case will be 1,000. Of course, with 1,000 elements, the time cost is not important, but neither is the memory footprint. But imagine if this is something more relatable to big data, like, for example, 10 million. I have a question. So this is similar. So let me just interrupt. I have a question. Is this similar to Jupyter Notebooks? Yes, it is similar. I was actually an early adopter of Jupyter Notebooks. The reason I prefer to use org mode is simply because I have the full power of a text editor. But it's the same thing, and you can even have bits and pieces on in Python and bits and pieces in R, and org mode is able to convert the data structures and pass the data structures across. But this is just the environment that I use. Of course, these techniques are you can use them with Jupyter or with a normal text editor. And so, for instance, here, what we have here is a list of 1,000 elements. And if you want to look in this list, so the average complexity to look for the list is 500 and 1,000, and the list is growing. But imagine, so this will depend on your use case. If your use case is just finding something. So imagine that you want to see, you have a list of individuals, and you want to see if that list if those individuals are referred. You actually don't need to do this. You can do something that will be substantially simpler, and you can use a set instead. And if you use a set instead, so set, oops, here it is. So here we go. Okay, so the set has a size of 5 because we only have 5 possible elements. 0, 0 if you go here, 0, 1, 2, 3, and 4. And so we have only 5 elements, which means that the data structure is itself extremely small, and which means that whatever it was the cost, now it doesn't matter because it's a much smaller data structure. But another example of why this can be interesting. Now imagine that you are doing something like this. Let me go back to the list. I'm just going to maintain the name just to be faster. And you are doing this. Okay. So now this is a list, though the name is not the best. So this is a list. And if it is a list, it's an append. Okay. And now if we do this, the list is again of a size 1,000. But if you want to find an element, this one is ordered. But imagine, and so it's easy. You can just could do just a bisection algorithm. But imagine that the list is not ordered. To search through the list, again, you have an average, a complexity of 500, and the worst case of 1,000. But if you use a set instead, the length is again 1,000 because you now have 1,000 different elements. But remember that a set in Python is implemented by a dictionary, and the lookup, if you are doing a search, a lookup, it's probably of complexity 1. So instead of needing to go through on average of 500 elements, you go into the hash table of the set. And you normally don't get clashes on most cases, but even if you get clashes, it probably won't be many. So the average case, it's constant at 1. Obviously, you are paying some penalty here in terms of memory because you need to maintain the hash key. But the point is that you have to make some decisions in terms of where you want to. Do you want to spend a little bit more memory, or do you want to gain time? And those are considerations that you have to do. And I have seen many problems where people are just using lists. They do some kind of testing with their code with 10 elements. Everything works fine. They put the code in production, and then everything stops. And actually, they know these are good programmers. The people that know what they are doing. They have a vague idea of the complexity of these data structures, but they did a small test, which is normal because you don't want to wait hours for a test. It worked, and then it didn't deploy. When you deployed, the performances, the system simply goes down. And so one of the things that I think it's important is to maintain this idea, at the very least, that okay, what would be the consequences of using these basic data structures when scaling up? But when you have a problem, the best way to try to understand where the problem is by profiling the code. One of the biggest mistakes that I see, and that happened with me countless times, is the belief that, oh, I look at the code and I'm smart enough to see where the problem is. And when I've run profiling tools, and Python has internal profiling tools, and I want to get into that in a bit, it would normally be in a completely unexpected place. Because it would be, for example, a case like the above, where I was searching in a list, and the list was too big, and suddenly a set makes a search go from extremely slow to a constant time. And so profiling is a good way to find the problems on the code. Python has standard profiling, which essentially will give you ballparks per function. But to be quite frank, and in the book you'll find a little bit about that. But to be quite frank, line profiling, which is something that you have to it's an external library. Line profiling is substantially more more useful, because whereas standard Python profiling will have a look at the function and give you an idea per function, it will you normally want it's when you go inside and you have a look at line by line that you can see what's really going on. So my honest suggestion is, if you have a profiling problem, you can run profile, because profile is extremely fast to run, and if you use a visualization tool, you might eventually, like SnakeVis or so, you might eventually get an idea where the problem is. But I personally, when I have a profiling problem, I go directly to line profiling. Line profiling instruments all the code, so it's extremely slow to run. But then you get a line-by-line breakdown of what's going on. And my two recommendations there would be use profiling. Don't think you know, or you spend as many hours as I did thinking that I knew what I was doing. Obviously, I didn't. And line profiling is better than standard Python profiling. Though, if you get used to standard Python profiling and you can run it in 5 seconds, which you can, you essentially just load the module, maybe you get something from that. But line profiling can be extremely, extremely useful. And another issue with big data that I think it would be important to consider is memory profiling. And Python memory analysis is tricky at best. So Python, and here goes another demo. Let's see how this goes. Python has a function called getSizeOf, which is in the sys model. Print sys getSizeOf. So, for instance, the size of an integer. And you see that the size of an integer is so this gives you the size of an object in bytes. You find this number, if you think about it, this number is potentially strange. So these are 28 bytes, not bits, bytes, to represent the number 10. And you might think, oh, what's going on here? 28 bytes for the number 10. There are, so the size of integer objects in Python can be a real minefield. There are many, many reasons, but one of them is that they are of unlimited length, so you can put whatever you want here, and they will. It's not that they are 34 bits or 20 or 32 bits or 64 bits signed or unsigned. You can actually do something like this. For instance, if you want to see the size of an integer, it can be complicated. Or a size of any Python object, you always pay for some object overhead, which I think it's around 20 bytes. So all objects will have an overhead of 20 bytes. And then with numbers, it becomes complicated because to decide how much space is allocated depends on the number side and so on and so forth. And if it's actually very small numbers between -10 and 120, they are actually pre-allocated for you, so it can be complicated. Another thing that can be complicated is the allocation of strings, because Python, and I'm talking here Python 3 exclusively, Python will look at your string, and remember, strings are not mutable, so when a string is created, we can see what's going on. Python will look at your string and decide the type of encoding as a function of your string. So if you use just US ASCII, you will pay the object overhead, and then it's only a byte. But if you use other kinds of characters, let me just put here, so let me just, this keyboard is an international one, so I'm going to put here a letter with an accent, say for example, so the A with Ångström. So notice this. So the size is 53 bytes, But I'm just now going to replace a character, this A by the A with the angstrom, which you find in Swedish. And it goes from 53 bytes to 77 bytes. And why? Because the internal representation changed, and it suddenly becomes a much bigger string. And if you use newer Unicode, it would be even bigger. And suddenly, depending on which characters you are using, you get a completely different. You change a character, and the string size quadruples. Of course, strings are not byte strings, and if we do this, this becomes smaller than if it's just a normal string. So this is get size of, and there are lots of pitfalls with Python objects, and I reinforce here Python objects because at some point in time we are going to use native objects, or going to discuss a little bit of native objects. And another thing that I would like to show is get size of with lists. So imagine the following list. Okay, it is a list with 3 elements. And if you now check the size of this, it's a size of 80. Every time you add an element, let's see what happens here. It got 8 extra. But now imagine that I replace this 4 with a string. And the size is still the same, which is strange, don't you think so? So it seems that every time we add an element, we are just adding 8 bytes, which is strangely similar to it's strangely similar to a 64-bit address. It's 8 bytes. It's a 64-bit address. When you use get size of, you are actually only getting the size of the. If it is a container, you get the size of the container. You don't get the size of the object. So you could have here an enormous object occupying gigabytes or whatever, and the size would only be 96. So the get size of only gets the size of the container object, or if it is a primitive object, it only gets the size of the object. And this can be a little bit worse, because think about foreign objects. You don't know, or extensions. Think, for example, an NumPy array, which, if memory serves me well, I should know this because it's in the chapter of the book, in the NumPy chapter. It might report the correct size or not. So you really, if you do a get size of an object, you only get the size of the of the encompassing object. If you want to know what's inside, you have to drill down. And interestingly, when you drill down, so if you want to get the size of this, so let's call this. And so my list, and we can do all sizes. So this is 0. No, this is actually, we can do all sizes. It's my list. Get size of my list, and then we would have to do for ln. So this code is wrong because it would have to be recursive, right? But for now, it's enough. My list, all sizes, plus equal ln. ln. Okay. sizes. Did a mistake here. Get size of LM sizes. Just see. I actually should. Sizes. What am I doing wrong here? Let me just. Just see what's going around here. C's get size of. Okay, 277. So we are summing up all the results. Okay. Okay, so we have the original list, and this one is 28, 28, 28. This is the string, which is 69, and then another 28. Now imagine, by the way, if you have lots of numbers, you are paying 28 bytes per number, or are you? Well, Python has a very interesting caching strategy. As a very interesting caching strategy for objects. And sometimes, so for instance, if you do something like this, Python, you notice that this is a 1 and this is another one. Python might be smart enough to notice, okay, this is the same value. This is not mutable, so we are going to use the same object. And if you do this, so what I'm asking Python is to give me the ID here, and you notice that. Let me just put the element here, just to make this clear. Okay. So this is 1, 1, 2, and so on and so forth. So if you see here, the ID is the same. So you can actually not do this, because actually only one of the elements there is only an allocation for one of the elements. So when you are computing the size of an object, you have to keep track of the object IDs that have already been accounted for. So here we would have to have, say, a dictionary of IDs that we have visited, and if it is already visited, we could not account for it. So it's not. So it's tricky, to put it lightly. But interesting. So, and these are problems that tend to disappear with both Python arrays, which I go a bit through the book mostly for completion reasons, and then NumPy arrays, because they don't use Python objects. They use typically built-in types like they are, first of all, they are homogeneous, so they have a single type. Notice that the list here we have several types. We have strings and we have numbers. But Python arrays, and more importantly NumPy arrays, they have types. They are homogeneous, so they all be numbers, and you'd have to specify if they are integers of 8 bits, 32 bits, 64 bits, signed or unsigned, and then you immediately lose. Imagine that instead of using integers, instead of using Python objects, Python integer objects, you use unsigned ints of 8 bits. Instead of 28 bytes, you only need 1 byte, which is, well, it's worthwhile. So arrays and NumPy arrays will tend to be considerably more economic. And there is other stuff that you can do. For example, if you know that you use only, so imagine that the values that you use are 0, 1, 0, 1, 2, 3. You can actually not only use a typed integer, but because you only have 4 values, every value only needs 2 bits, and you can put 4 values. You can pack the values yourself in an array. So that means that it's not 1 to 28, but it's 1 to 112, the memory gains that you have. And that actually has profound implications on performance, not only memory, but only on CPU usage.